Hello everyone, so today in this video we are going to discuss this question gardener entry which was asked in Codeforces round 748 Div.3. In this question we are actually given a tree which is undirected and is also connected, and the tree which is given to us is non-rooted, that is no root is present in the tree. What we have to do is we have to do actually k operations, and in each operation we have to remove the leaves of the tree. For example, suppose in the first operation I remove all the leaves of the tree. In the second operation I therefore the remaining nodes which are remain in the tree, some of them out of that will become leaves. Then in the second operation I remove all the remaining leaves of the tree. In this way we have to do the operations. Let's understand this with the help of this example. In this example what we can see is the tree is actually non-rooted, therefore the leaves are actually this 14, this 11, this 12, this 5, this 6, this 9 and this 10. These all are leaves. In the first instant I decided to remove all the leaves. If I decided to remove all the leaves, that is actually we are given k operations. Let's say in this question k is equal to 2. If k is equal to 2, then at k is equal to 1 I decided to remove all the blue marked nodes. So if I removed all the blue marked nodes, then our tree will look something like this. So k is equal to 1 operation, then now comes k is equal to 2 second operation. In the second operation I decided to remove the leaves. So now the leaves are 13, 3, 4, 8. If I now remove all those leaves, then our tree will look like something like. Okay, then our tree will look something like this only. So after two operations, we are left with this tree only, and therefore the answer will be 3 in this case, because only 3 nodes are present in this tree. So this is how what the question is saying. And some of the special cases are, we can, if there are no vertices, let's say, let's also understand this with the help of example. Let's say we are given k is equal to 8, and we are given the tree something like this, 1 2 3. In the first instance I remove this one and this 3. In the second instance I remove 2 also. So in the two operations we can see that the no roots are actually remain. So remaining 6 operations are actually useless. So so answer in this case is 0. In the second special case is applying an operation to a tree of one vertex. Yes, okay. If only one vertex is given to us in the tree, suppose the vertex is 1. So in one operation we can remove this vertex and the answer is 0. So if only one vertex is given to us and the k is equal to 0, then answer is 1. And if k is equal to 1, then answer is k is greater than equal to 1, then answer is 0. But in this question we are given that k can't be equal to 0. Here you can see that the k can't be equal to 0. So what we can say is that this answer is equal to 1 can never be the answer. If number of nodes is 1, then answer would definitely be 0. And in the third test case we are given that if there are two nodes, suppose 1 and suppose 2. So so in one operation only both of them will get removed out, because both of them are leaf nodes, and in one operation after the one operation answer would be 0. So this is the question. Let's understand the approach of this question. Okay, so this is the tree which we are given to us. So what we will do is, first we will make a vector called connections. Let's make a vector named connections. This vector is actually of size the number of vertices. So I will make this vector of size 14. So this is my vector of size 14. Let's say I named it at connections. So what we can see, if we observe one, let's traverse this array connections. If we see one, we can see that from one there are two actually edges which are passing through one. So I can say the degree of one is 2, or I can say you can say instead of degree you can also use the word connections. The number of connections of one are 2, so I will put 2 here. In 2 we can see the four actually edges are passing through 2, or I can say are coming out of 2. So number of connections or the number or degree of 2 is 4. Similarly for 3 we can say it is 3. Similarly for 4 we can say it is, here it is 3. Similarly for 4 we can say it is 3. For 5 we can say it is 1. For 6 it's also 1. For 7 it's 2. For 8 is 3. For 9 it's 1. For 10 it's 1. For 11 it's 1. For 12 it's 1. For 13 it's 2. And for 14 it's 1. So this is our connection array which we will use throughout the question. Another important thing which we have to observe in this question is that there are no one whose connections is 0. You can see in this array there is not even a single value in 0. The values are 2, 4, 3, 3, 1. These types of values are only there. There is no value 0. So we have to think when the value should be 0. You can easily be able to think of, if there is only one node, let's say node is 5. So you can see that let's say 1. So you can see that there are no edges which are coming out of 1. So we can say the number of connections is equal to 0. Number of connections is equal to 0. So when we can say that the number of connections is 0, so my question to you is it possible that there are more than one nodes present and the number of connections is 0? You can say yes, it's possible. Let's say there are two nodes. This is one node and this is second node, and therefore there are two nodes present. And we can say, okay, here for one the number of connections is 0, and for 2 the number of connections is 0. You are correct, but you can see that in this question we are given to us that the graph is a connected graph. The graph is a connected graph. So we can say that this type of graph isn't possible in our question. This type of graph isn't possible in our question. It means the graph can't be disconnected. So what we can say is number of connected components. According to this question I'm saying number of connected components can only be 0 if and only if the number of connected components is 0. This implies only one node is present. Only one node is present. So this is an important observation. Let me write the observation. Observation is if number of connections become 0, if number of connections become 0, this implies only one node is present. Only one node is present according to our question. This observation is very much useful in while writing the code. So this is the observation. I am again repeating the observation. If number of connections become 0, this means only one node is present, and vice versa. If only one node is present, it means the number of connections become 0. So what we have available to is we have available two things. One, the observation which we had made, and the connections array which we had made. So what we will do is we will traverse the array. We will traverse the array from left to right. First time we will traverse the array from left to right once, and we will see whether any value 0 is present or not. If any value 0 is present, it means we are definitely sure that only one node is present. So we can say, okay, only one node. We will traverse the actually connections array and we will check whether 0 is present or not. If we found that 0 is present, it means we are actually confirm of 2 to 3 things. The first thing which we are confirm out is only one node is present. Only one node is present, and actually that node, therefore the answer in that case can either be 0 or can either be 1. But we had discussed that answer can never be 0, because if only one node is present and answer is 0, this means k should be equal to 0, and in the question we are given that k should be greater than equal to 1. It means only one node is present and k is greater than equal to 1. So we have to at least remove one node. So when we are traversing the connections array for the first time and we found that 0 is present, so we will say, okay, 0 is present, this means answer should be equal to 0. So what our case is, if while we are traversing for the connections array for the first time, if connections of I is equal to 0, or I can say, actually, instead of writing connections of I can also write it as connections of 0 is equal to 0. If connections of 0 double is equal to 0, this means we can say, if connections of 0 double is equal to 0, this means we can say that the answer is 0. Answer to this question is 0. This is our, let's say, case number 1. Case number 2 which we can make is, we are actually given k number of operations. Let's say we say that n is less than equal to k, that the number of nodes are less than equal to k number of operations. If number of nodes are less than equal to k number of operations, it means all the number of nodes will get actually destroyed after the k operation, or we can say even before the k operation. So in this case also answer is 0. In this case also answer is 0. If n is less than k, then answer is 0. So we had come up with two things. Connections of 0 is 0, it means answer is 0. And if n is less than equal to k, then answer is 0. So now, so let's see how we will now move further. So we have an array of connections and in which there are no zeros present. And our k is also not less than n. So what we will do is, before I am actually going to tell you a sequence of loops. Before going into the sequence of loops, first we have to make an array. First we have to, let me actually clear out some space so that it would be easy for me to tell you the approach. Okay. So first we will do is, again we will traverse the connections array and we will see which nodes are having value 1. We can see that the node having value 5. Node that is 5 is having number of connections 1. Node having value 6 is having connections 1. 9 is having connections 1. 10 is having connections 1. 11 is having connections 1. 12 is having connections 1 and 14 is having connections 1. If these nodes are having connections 1, it means I can definitely say that these are the leaf nodes. So let's say I make another array. Let's say I name it as special SEQ, SPEC SEQ. Why I use these naming conventions, because when I will see you my code, the code I have written, I have used these names also, so it will be easy for you to correlate. So in this I will put the name 5, 6, 9, 10, 11, 12, 14. So 5, 6, 9, 10, 11, 12 and 14. So these are the nodes which are actually having one connections. So let me, okay, so what I will do is I will actually apply a for loop. I will apply a for loop on what? I will apply a for loop on special sequence. I will apply a for loop on special sequence. I go through the each node which is present in special sequence. So I will write this is actually for each node in special sequence. For each node in special sequence, I will traverse each and every node. So what I will do is, for each node, this is the most important part. So carefully understand it. For each node I will traverse, I means okay, we will traverse adjacency matrix of that node. We will traverse ADJC, we will traverse adjacency matrix of that node. This is the most important thing of this whole section. So what we will do is, we will go to for each node. First we go to 5, then to 6, then to 9, then to 11, then to 12. When we are going through each node, we will traverse the adjacency matrix of that node. What we will do is, okay, so first we will go to 5. You can see that the 5 is present here. In the graph you can see that the 5 is present in the lower section. You can see I have marked 5 with green. 5 is present here. In the adjacency matrix of 5, what you will find? You will find is, in the adjacency matrix of 5, 4 will be present, and 6, only 4 will be present. In the adjacency matrix of 5, only 4 will be present. So what we will do is, we will traverse the adjacency matrix of 5. While traversing the adjacency matrix of 5, what we will find? We will find 4. So as we are now removing 5, it means the number of connections of 4 will be reduced by 1. So what I will do is, I will traverse the adjacency matrix of 5. I found 4. So when I found 4, I will say okay, as I am now removing 5, so number of connections of 4 will be reduced by 1. So in the connections array, you can see the number of connections of 4 is 3. So we will remove that 3 and will made it 2. We will say okay, now the number of connections of 4 will be reduced by 2. Why the number of connections for 4 will be reduced by 2? Because we are actually removing the node 5, because of which the number of connections of 4 will reduce to 2. So again I am repeating this, I am removing 5, therefore the number of connections of 4 is reduced by 1. So I had made the number of connections of 4 reduced by 1, so it becomes 2 now. Now after that I will move to 6. After that I will move to 6. So when you can see 6 is present here only. This is 6 actually. So what I will do is, I will say okay, I will traverse the adjacency matrix of 6. When I will traverse the adjacency matrix of 6, I found 4. I say okay, what I will say is, I found 4. So I will say is, the number of connections of 4 further reduced by 1. So here the number of connections of 4 are actually 2. So I will make this 2 actually 1. So now the number of connections, so let me erase it and write whole properly. So now the number of connections of 4 becomes 1. So now the number of connections of 4 becomes 1. And as soon as the number of connections of 4 becomes 1, what do you think? You are thinking that as the number of connections of 4 becomes 1, it means now the 4 becomes a leaf node. Now the 4 becomes a leaf node. So you have to remember this in mind. Now the 4 becomes a leaf node. So I actually forgot one statement here. Before writing, actually we are actually traversing for a special sequence array. Before traversing the special sequence array, we have to apply one more for loop, which is above this. For I is equal to 0 to I is equal to k. Let me make it more clear. Yes, huh. So what we will do is, before actually this for loop, before actually traversing the special sequences, what we will do is, we will first do for I is equal to 0 to I is equal to k. Okay, so let me recap it once again. Why I am doing from I is equal to 0 to I is equal to k? Because we have to actually do the operations actually k times. Later in the video you will be able to understand how this whole process going on. First you will only put that much into the brain that we are actually traversing from 0. We are actually making a loop from 0 to k, because we have to do k operations in every operation. in the I is equal to 0th operation, then I is equal to 1 operation, then I is equal to 2 operation. For every operation, we are actually traversing the special sequence. And for each node in special sequence, we traverse its adjacency matrix. And while traversing this adjacency matrix, what we are doing is, you can see in the video that while traversing the adjacency matrix, here you can see I traversing the adjacency matrix. First I will see 5, then I will see 6, and then traversing adjacency matrix, I am actually reducing the number of connections. So till that point I found that 4 now becomes a leaf node. So what I will do is, here I will make another vector named vk. Here I will make another vector whose name is vk. What I will do is, as soon as the node becomes leaf node, I will put that into the vk. So initially I put vk dot pushback 0 because I found that, okay, 4. Okay, so what I found that the number of connections of 4, here you can see the number of connections of 4 becomes 1. Therefore, I say that, okay, if the number of connections of 4 becomes 1, so it becomes a leaf node. So I say, okay, vk dot pushback 4. Now I come to 9. I see that in the adjacency matrix of 9, 8 is present. So I reduce the number of connections of 8 by 1. Then I will see, okay, 10 is present. Then I reduce the number of connections of 8 by again 1. So we can see that the 8 also becomes the leaf node. So 8 also, as soon as 8 also becomes a leaf node, so number of connections of 8 also becomes 1. So number of connections of 8 also becomes 1. What we will do that, while we are we also have to maintain a line that before traversing this special sequence, what we will do is, we will actually traverse this special sequence 2 times. First, when we are traversing this special sequence, what we will do is, we will say, okay, those who are having the value of their nodes, that is those who are having the connections 1, let's make their connections -1. Because we have actually used that up. Okay, what we have done is, we have traversed the array. We found that, okay, these are having the special sequence 1, so we will put that in our bag that is named special sequence. Now we will do that -1. Okay, now these 5, these 6, these 9 and these 10 are now having the number of connections as -1. This 11 also has number of connections -1, this 12 also, or this 14 also. That now these are having the connections as -1. So let's move further. Now as we can see that the 8 having the number of connections as 1, therefore 8 also becomes our leaf node. So we also push back 8. Similarly, we can see, if now we will go to 12, we will say, okay, 12, then we will go to 11, and then we will go to 14, because of which we can see that the 13 and 3 also becomes leaf node. So let me also make that 13 and 3 also becomes leaf node. So this 3 also becomes leaf node, and 13 also becomes leaf node. So number of connections become 1. So I will also put 3 and 13 in this. I will put 3 and 13. So I will say, okay, now my new vector, which only contains the nodes which are having connections 1, is now become vk. So what I will do is, I will do special sequence, special underscore sequence is equal to vk. Now I will take this step. So first I will apply the operation k times, then I will make a vector vk which will store the special sequence for every time. Now what I will do is, I will traverse the special sequence. Actually, before I is equal to 0 to k, I had already traversed, before I is equal to 0 to k, I had already traversed special sequence once and found all the nodes which are having the connections 1 and put that into the special sequence array. After that, I will traverse the array I will traverse a loop from 0 to k, because we are performing the k operations. 0 to actually less than k, because we are performing k operations. I had made a vector vk. which will from now onwards will store my all the values which are having the connections 1. I will traverse special sequence. For each node in special sequence, what I will do is I will traverse the adjacency matrix of that node and I will reduce the number of connections of that accordingly. If I found that at any instant the number of connections become 1, you will be able to what I do is what I said to you is I will traverse special sequence 2 times in the loop. Once is this for special sequence for each node in adjacency matrix. Before that, I will traverse this once again. Before traversing that, what I will do is I will mark all the connections of the nodes which are present in special sequence as -1. All the nodes which are present in special sequence, I will mark the connections of all that nodes as -1. Again, I will traverse the special sequence, and for each node, what I will do is I will traverse its adjacency matrix and reduce the connections. If I found that the number of connections become 1, it means I will push back it into VK. And when we are going back into the loop, what I had done is I will okay, now special sequences become VK. Now new special sequence is ready to us, and now loop is going on. Now again what we will do is we will mark now the special sequence contains all the terms which are present in VK. Now we will mark all of them with -1. Now we will traverse the special sequence for each node. We will again traverse the adjacency matrix and reduce all the connections by 1. And after the case steps are done, we will traverse this connection array and see how many nodes are not having the connections as -1. We will find that, okay, let's say 5 nodes are not having the connections as -1. So our answer is 5 because all other nodes are having the connection as -1. So at the end, we will traverse the connection array and check whether how many nodes are not having the connections -1. One check you have to keep in mind that you are saying that we have to put all those into VK who are now having the connections as 1. But it might be possible that some becomes the connection 0. For example, let me take you with the example that if the node is of this type 1, 2, 3, 4, 5. Let's say this is my graph. This is my tree actually. In first instance, this becomes removed, this removed, this removed, this removed. You can see that the connections of 1 become 0 after that. So if the connections of one becomes 0 after that, we have to keep a check here. While we are keeping a check that whether the connections become 1 or not, we have to keep a check whether the connections become 0 or not. If the connection had become 0, it means only one node is present. Then only one node is present, and then we will check whether we have covered the whole I is equal to 0 to I is equal to k, I is less than k or not. If we had covered the whole loop, then the answer would be 1. If we had not covered the whole loop and the loop is yet to be covered, it means in the upcoming process, we can see that node is actually got removed. So in that case, the answer would be 0. So let me dive you to the code section so that you will be able to understand the how we will write the code for it. So what I will do is first I had made graphs and connections. Here graphs represent the adjacency matrix and the connections represent the number of connections each one is having. I had made a check if n is less than k, see out 0 and continue. If n is less than k, see out 0 and continue. After that, what I will do is I will say, okay, if I will make a count 1, and if I will say if connections of I is 1, then increase the count, and I put all that in special sequences. Putting all that in special sequences. Now what I do is if count 1 is 0, it means no one is having connections 1. If no one is having connections 1, it means there should be nodes having the connections. There should be a node having a connection 0. So if k is greater than 0, I had c out 0. Else if k double equal to 0, I have c out 1. You can remove this case that if k double equal to 0, then you can c out 1. I have again wrote the same condition which I did in k is less than k, c out 0. You don't have to write this section again. You can remove this. After that, what I had done is I traverse from I is equal to 0 to I less than k. Then I will traverse the special sequence. You can see I will traverse the special sequence, and I had made what? I had made the connections of special sequence -1. And you know that what the special sequence contains. Special sequence now contains all the nodes which are having -1. Sorry, which are having 1 as their connections. I will make a vector vk underscore new which will contains my new nodes having connections 1. I will again traverse these special sequences. I will traverse the adjacency matrix of each of one them. And what I will do is, while traversing the adjacency matrix, I am keeping a check. If connections become 0, then I had made is single plus plus and then break. And later on what I had done is, if single is, then single plus plus break, this I had done. And if single is greater than 0, that is, I found a single node and I is less than k minus 1. It means there are more operations which is left to me. So I will see out 0. If single is greater than 0 and I had already completed the k operations, therefore I is equal to k minus 1, then I will see out 1. If I won't found any node having connections as 0, that this is the node having connection 0, so I will say okay, I will see how I will push back in vk underscore new. I will push back who are now having the connections as 1, and at the end what I made is special sequence is equal to vk of new. Special sequence is equal to vk of new. Then I will say okay, who are now having connections greater than 0, or I can say who are not having the connections as -1. Find out their count and tell the count in the answer. So this is the approach to this question. If you like this video, do